Good morning, everyone. I'd like to welcome you on the UHP session today. And without any further ado, I'll start with my presentation. I'm a PhD candidate at the University of Calgary, and I'll be talking today about the tensile strength characterization by 4-point bending simplified method with an inverse analysis for carbon nanofiber infused ultra-high performance fiber reinforced concrete. I'll start with a short introduction, and then I'll talk about the carbon nanofiber infused ultra-high performance concrete, and then the tension testing methods, and then I'll talk deeply about the simplified method that I am using here, and then the experimental program, results, and finally the conclusion. So we all know that UHPFRC is discovered in 1980s, and it's mainly characterized by the superior durability and the superior mechanical strength. More specifically, it's characterized by compressive strength that is in excess of typically 150 megapascal, and that is attributed to the materials or to the using the low water to binder ratio, removal of the coarse aggregates, which means removal of the weakest link in the concrete, which is the transition zone between the aggregates and the matrix, and the usage of pozzolans and superplasticizers. The second is that it has a post-cracking tensile strength that is typically in excess of 5 megapascal. And that is due to the usage of or the inclusion of high-strength fibers, mostly steel fibers, as you can see here in the picture, and the reduction in the pore sizes, which are stress erasers. So by a reduction in the pore sizes, we are reducing the stress or actually making the stress more uniform in the matrix, which makes the material more stronger. Now, why carbon nanofiber? So we know that the inclusion of steel fibers, which is typically at the 2% by volume, makes UHPFRC have a steel-like strain hardening response, as we can see in here. And therefore, the material is called tension hardening UHPFRC. If the volume is not enough to give the material the steel-like strain hardening response, then the material is called softening. However, the problem is that the spacing of these steel microfibers is relatively large and they are expensive. So this makes them most effective in the post-cracking stage. As a result, the inclusion of a low-cost nanomaterial is introduced as a suggestion, and so comes the carbon nanofibers. So carbon nanofibers are graphite material with mainly superior tensile strength and high conductivity. What does the carbon nanofiber do for the UHPFRC? It improves its durability to above 100 years, and most importantly, it increases the tensile cracking strength as well as the tensile hardening ratio. Now, speaking about the tensile cracking strength, it's generally hard or challenging to characterize the tension properties of fiber reinforced concrete and in particular UHPFRC. The two most widely used methods in the literature are the direct tension test and the bending test with a point-to-point inverse analysis. In here, we can see a direct tension test, and it's like the direct tension tests are generally, they impose fewer bending stresses on the specimen, but they are in turn hard to conduct. On the other hand, the bending tests are easy to conduct, but they require sophisticated post-processing to determine or predict the uniaxial tensile behavior. So every method has its advantages and disadvantages. Now, what about the method I'm talking about? It's a simplified 4-point inverse analysis, which ensures that it's a simplified method, but at the same time, it ensures the accuracy. So this method is based on extracting 4 cardinal points from the load deflection curve, experimental load deflection curve. The first point is from the first 2 points are from the elastic behavior, and they correspond to the intersection of the graph with the 75% and 40% of the initial stiffness. The third point is for the hardening behavior, and it's the crack localization point. Here it's taken as 97% of the maximum load. It's the intersection also, or the border point between the hardening and the softening behavior. The third point, or the fourth actually point, is from the softening behavior, and it's 80% of the crack localization point. Now this method, just like any other method, it has its limitations. As per the code, the material has to be hardening, which means the ultimate strength has to be at least 10% higher than the elastic strength, and this is satisfied for the material we're using here in this research. And P2, as you can see here, which is the 40% of the initial stiffness, has to be less than P3, which is the crack localization point. Now the method, like the reference of this method also imposes another or a third limitation where the tensile ultimate strain has to be at least 10 times greater than the elastic tensile strain. Now this condition is not satisfied for the material I am using, as you can tell. Here it's a graphical representation of the load deflection curve of this method. It's the codified graph. These cardinal points are taken and inserted into some equations, and finally, this is what we might end up having, cracking stress and strain, as well as an ultimate stress and strain. Now, as for the experimental program, in here we tested unnotched specimen of the size of 75 by 75 by 300, as you can see here, and we used 2 LVDTs, one at each side. We used 3 different batches, but they all were for the same mixed design. Concrete was put from one direction, casting orientation was the same as the testing orientation, curing was standard curing. As I mentioned previously, we used CNF-UHPFRC with straight steel fiber at a content of 2% and 0.3 by 13 millimeters dimensions. Tested the specimens at the age of 28 days using 100 kilonewtons machine. And the loading rate was divided into 2 stages as per the ASTM C1609. Now, what about the results? As I mentioned previously, the code implies that the P3 has to be greater than P2, and this is satisfied in here. However, when we look at the graph, we can tell that this is S0, this is P1, which is the 75% of the initial stiffness, and this is P2, which is the 40% of the initial stiffness. You can see that P1 and P2 are in the softening region. They're not even in the hardening region, and they're like P3 is actually greater than P2, so the code limit is satisfied. However, the method yields, when we are doing the inverse analysis, unrealistic numbers. This is especially true for the ultimate portion. In this graph, you can see a load and deflection curve versus the time, and you can see here's the onset of the change in the loading rate and the onset of the cracking. That was the first sample. Now the second sample, in here you can see that the P3 is actually less than P2, and by default when P3 is less than P2 the method is not applicable, but still you can see that the 75% of the initial stiffness as well as the 40% of the initial stiffness are also located in the strain softening and not in the strain hardening region. And that's a comparison between what we are getting as a typical load deflection curve versus the codified load deflection curve, and similar results where unrealistic results are received or calculated for the ultimate portion. Here we can see some of the tested specimens. And what does this mean? Now when the limit of the code is met, the P1 and P2, which are the 75% and the 40%, are located in the softening branch, which makes delta 3 less than delta 1. And therefore, when we are putting these values in the equation of the inverse analysis, we're giving a negative value, which means the method is not applicable. And whenever P3 is not greater than P2, by default, the method is not applicable. So as a conclusion, we can say for that the choice of the 75% and the 40% secant stiffnesses limits the range of the concretes that can be modeled. What does that mean? So if the 90%, for example, and 95% of the secant stiffnesses were used, this concrete could have been modeled. However, it's going to be harder or more difficult. Why? Because the intersection, because it's going to be hard to extract a suitable point from the experimental curve because of the low intersection angle between the two curves, which is the secant stiffness and the experimental curve. The bottom line, it's a simplified method, but very limited. And this brings me to the end of my presentation. Thank you for listening, and I welcome any questions.